Good morning, students. Today we shall discuss, or rather, we shall design the BJT amplifier that we discussed or designed theoretically on in our last lesson. Today I am going to simulate it right in front of you with a Multisim software. You can use any software, but Multisim is very common and educational version is also available. All of you should have this software to become a successful engineer. Anyway, uh, many of you may be conversant to this software, but some of you, if you are not so conversant, so what I'll do go a little slowly than normally if I would have done it myself. So that you can follow what I'm doing. And from our last lesson, this design parameters I have just copy pasted here, and the designed circuit also I have copy pasted here, right? So that both of these are in front of me. At the end, I will remove these pictures. First is I have to get a BJT. So if you go to this place transistor component, BJT is a BC547 is a NPN transistor. Go to NPN. Then their list is alphabetic. Go to BC547. BC 5455. This is 54. This is 547. Then press OK. Your BJT is placed here. Right? You can close it. This is BJT 547 right in front of you. Now what you can do, now I need a power signal source. So I go to sources, go to AC voltage source. I choose a AC voltage source and I bring the AC voltage source here, right? Close it. And this AC voltage source, I need, my design frequency is 1 kilohertz. It is already at 1 kilohertz. I think you can see it. And its voltage is very high. I do not need some voltage, this many voltage. I'll bring it down to say 50 millivolt or something like that. So instead of 1 volt, sorry, if you double click on the symbol, this page will open. Here you can change all the values. I make say third, right? Label also I change to VS because that is my level, right? So this becomes 30 millivolt RMS. I wanted RMS value, 30 millivolt RMS, 30 millivolt time delay factor phase analysis phase tolerance. Sorry, this gives in peak to peak value only 30 millivolt peak, 30 millivolt peak. I make it a little bit higher, maybe 50 millivolt peak. 50 millivolt peak. This does not give the RMS value, phase analysis distortion. This does not give it phase analysis value. So this signal voltage source. This is the signal voltage source, AC voltage source. If I bring an AC voltage source, close it here, this also gives voltage peak, so I do not need it, right? So this is the voltage source. Then I need a capacitor CI, which is 330 microfarad. So I go here, go to the capacitor, I go to 330 microfarad. 330 microfarad. This is 330 micro, right? So a 330 microfarad capacitor. It becomes, I make a little space so that it is easy to see. So I connect it here. And of course, I need a ground connection. That is most important. So power sources, I need a ground connection. I need a ground connection here. Then I need actually um, I need two resistances R1 and R2. R1 was 10.27K. So I bring any resistance. Even after bringing, I can change the value. 10.27K. Let me see whether I can have 10.2K. So this is the resistor. And if you want to, this resistance in my drawing, this resistance is vertical. So you right click this, you get this options of changing them. This is R1 and its value as per my requirement is 10.27. So I double click, change the value 10.27. Right? Then I need R2 is as R2 is 2.2K. I don't have to once again go to component placement. I can just copy paste this, Control C and Control V, another resistance. And this resistance should be 2.2K. So I change the value to 0.2K. Right? Now these two should be connected together like this. Now this capacitor also should be connected here. This is the input and these resistors will be connected to common. Resistor will be connected to VCC, DC power supply. So DC power supply, power sources, DC power. I bring the DC power here, right? And this is 12 volt. I make it 10 volt. Make it 10 volt DC power, right? This DC power should be connected to common. So I just place another common symbol here. Right? Then this there should be another resistor RC here. RC value is 1K. So I copy this resistor and paste this resistor here. This value is 1K. 1K. And its level I make RC. So RC is 1K. And this RC is connected to the transistor. Right? And RC is connected to the transistor. And this is voltage is connected to the resistor, and from here also it is connected to this, right? Point is connected to the transistor base. This point is connected to the transistor base. At the emitter, there is another resistor of RE 220 ohm. RE of 220 ohm. E value is 220 ohm. This is also connected to common, connected to the transistor emitter. I need a capacitor here, CE, which is equal to 100 microfarad. So I just copy paste this. And with a right click, I turn it by 90 degrees so that it looks like me. And it is, its name is CE. So I make it CE. Its value is 100 microfarad. Farad. So micro, cannot find a micro symbol here. So what I'll go to replace and replace by 100 microfarad. Here I have 100 microfarad. 100 microfarad capacitor here. This capacitor should be connected to the transistor emitter and it should be connected to 100 microfarad. Then I have this load capacitor. C output is 1 microfarad. So this label I make CO and value I make 1 microfarad. 1 microfarad. Let me go to, I cannot find out the micro symbol. So I go to 1 microfarad, 1 microfarad, 1 microfarad. So this is 1 microfarad. Want it to be like this. CO, its level is CO. CO, 1 microfarad. This one will be connected here. This one will be connected here. Right? And the load resistance will be connected here to the capacitor. Load resistance is RL connected to the capacitor here, and this is RL, and RL is 10K, if I remember correctly. This is RL, and its value is 10K. It's connected here. Right? Then my output is taken out from here. So what I shall do, I shall place a connector here. So anyway, the output is be taken out of here. Now, now I put the instruments. In fact, I have to cross-check ICQ and VCEQ. These two are very important, right? ICQ is the current flowing through this line. So I have to put a multimeter here. So what I do, I is a little up and put the capacitor, take the capacitor also up. Let me see whether I can put the multimeter here or I'll take the whole thing upward. This one, this end also I shall take upward. I shall put a multimeter here, or multimeter for measuring the indicator for measuring the current, right? So here I have instruments. This indicator. Here I have to measure the current, or I have to measure the current. Here I can make both AC and DC, and display level I make ICQ. Right? So this is ICQ, and I remove that unnecessary displays. This is ICQ. I write it here. This is ICQ for measurement. I shall also measure the collector emitter voltage, right? So I just take this multimeter little bit above, it allows. I shall also measure the collector emitter voltage, and from there I shall take a voltmeter. I shall take a voltmeter vertical. I take a voltmeter, I make a little space here. This voltmeter level is VCEQ. VCEQ, and display. I remove this. This is VCEQ voltage. I can make AC, DC, whatever I want. So this is a voltmeter which will correct my VCEQ. So ICQ, VCQ, we have to measure. And now my output is taken out from here, right? So in order to see how the output looks like, I need an oscilloscope. I take this writing here. I need an oscilloscope. This is an oscilloscope. The oscilloscope I connect to the input signal. Right? Other end I connect to the output signal, right? The color of the input I make blue so that we can identify the two signals. So have you done everything? I think we have R1, RL. This is the ICQ, DC current, CQ, C current, and this is VCQ, voltage, and this is ampere. It is uh, so small written. Let me see whether it is shows it is ampere. Then what I do? This is ammeter. This is a voltmeter. This will measure ICQ. This will measure VCQ. So oscilloscope is connected. Then I switch on the oscilloscope display here and start running the signal. So you see, this is the signal. Now, input signal blue line is almost not visible. That is because the Y scaling, now you can see the, and also this is the input signal and this is the output signal. One is the output signal. If I take another scale, no, it goes out of oscilloscope. So here I find the output signal is, here my oscilloscope scale is 2 volt per division. So 1, 2, 3, and 3.5, approximately 3.5 division, and 2 volt per division into 3.5 division is 7 volt peak to peak. So output is 7 volt peak to peak. If I just place here, there's a comment here. VO is equal to 7 volt peak to peak, right? And V in one, this is 100 millivolt per division. I make it larger for the sake of measurement. Now it is 20 millivolt per division, and number of divisions is 1, 2, 2.5. Here also 1, 2, 2.5. So 5 divisions and 20 millivolt per divisions and 5. So input is about 100 millivolt. So VI is approximately 100 millivolt, 100 millivolt, 100 millivolt peak to peak. So what is the gain you see here? Gain is 7 volt peak to peak divided by 100 volt peak, millivolt peak. So 7 volt is 7,000. 7,000 by 100. So you get a gain of AV of approximately 70. So this is how my, so I can say the amplifier is working. Now let me see, cross check the VCQ ICQ. ICQ should be 4.7 milliampere. So here, what is the VCQ? It is 4.801 milliampere. This is okay. I mean, you can still fine tune it, but it will not make much difference, that I can tell you. It is pretty good. So This is how you design this amplifier and test it. In fact, maybe I'm not sure, you may have this test experiment in your laboratory also. In laboratory, sometimes you have to do it on actual hardware, sometimes, in some cases, you do it on simulation. So, this is how an amplifier. So, what we have learned, we have learned what is the what are the small arithmetics and formula and empirical relations required in an amplifier. Then in the next lesson, we actually took BJT 547 and with calculation, we have arrived at all those values. Now, to complete the cycle, we actually tested this on simulation and we find, yes, the simulation works fine. One small thing is left that we shall do in the next lesson, which is called performance analysis. In fact, you have to actually measure the gain. You have to measure the input impedance of your amplifier. You have to measure the output impedance of your amplifier. You have to measure the frequency response. That means from which frequency to which frequency your amplifier will work. Because if you are going to really design an amplifier and sell it in the market, you have to specify all these figures. Finally, you will have the amplifier ready. So that performance analysis calculation, it is not very lengthy, just 2, 3 small points. And testing that performance in this amplifier, we shall do in our next lesson. And then I think you will be all very happy with the amplifier.